Hello everyone, my name is Cheng-En. Today I'm going to give a talk about synchronous message passing with priority. Priority is crucial in different contexts. Our long-term goal is to develop a functional programming language for real-time systems. That system software can be a airplane controller or autonomous vehicles or some other online streaming services. And our starting point will be using concurrent ML. So for CML, CML is a synchronous message passing language. It provides a robust primitive tips for programmers to construct a multi-threaded code under the message passing context. And the challenge here is we want to know the definition of priority in a synchronous message passing language. And to help you better understand this challenge, let's start to look at some CML primitives and see what it provides. And begin, we have an example of the communication in message passing under the CML context. This is a diagram. We use a notation. The black line stands for a running thread, and the green line stands for a waiting thread. Red line stands for a blocking thread. In this example, we have two threads, T1 and T2. At the beginning, T1 is up and running. It executes until it performs a send action. The send action will send the value V to channel C. After T1 performs the send action, it blocks. And so once T1 blocks, T2 has a chance to up and running. As we can see, T1 is blocked and T2 runs. It stops until it performs a receive action. The receive actions here is to receive from channel C. Note that this is a pairing of send and receive, both try to act on a channel C, so we can pair them together. Once we pairing them together, and the value V will be sending from T1 to T2. Now, the T1 after the communication, T1 gets unblocked. It had a chance to be scheduled, and T1 can be scheduled. Once it is scheduled, T1 will be allowed to get up and running again. And the main observation in this example is since synchronous message passing is synchronous, and threads blocked, and so the communication patterns can have a direct impact on which threads get executed. After we understand the example, let's look at some events, first-class events, or sometimes we call protocols. CML provides first-class events. These events are the description of communication protocols. And protocols are executed when those events is synchronized by a thread. Note that the events is a first-class value, so it doesn't have to synchronize. Threads can construct an event and send that event to other thread before the synchronization. The send and receive, what we have seen so far, is basically a synchronization on a send event and receive event. It can be expressed in terms of this sync on send CV and sync on receive EVT on the channel C respectively. So these are the first class event in CML. Let's consider adding a priority to this message passing. We started to adding this priority with a traditional approach, which is associate the priority levels with a thread. And let's look at how it goes when we adopting this approach in a CML. First, we in this example we have three threads. The first thread is TH. The H here stands for high. It's a high priority thread, and we have two low priority threads in this case. And at first, of course, the high priority threads has a chance to be the first to up and running, to be the first to run, and when it runs, it construct a send event, and the send event is basically try to send a value v to channel C2, and we bound that event to EBT1. Now, the high priority thread sync on a send event, try to send that EBT1 to C1, channel 1. And once the high priority thread sync on the send event, it blocked, right? And we got a chance to switch to the low priority thread. Let's assume we switch to this low priority thread, and the low priority thread try to sync on a receive event from C1, and since this receive event from C1 is a pair with this send event, we can pair this send and receive together. As a result, the EBT1 will be sending from high priority thread to this low priority thread, and we store that EBT1 as a EBT2 in this low priority thread. After this communication, the high priority thread will be allowed to resume to be up and run again, and it executes until it performs some blocking action. For example, it can be doing an I/O. For some reason, it performs a blocking I/O, and now we have a chance to switch to a low priority thread. And let's consider the low priority thread sync on EBT2, and now we have another chance to switch back to a high priority thread. And when it sync on at EBT1, the high priority thread gets blocked again. Now the only thread left here is a low priority thread at the bottom, so we get a chance to switch to the low priority thread, and it sync on the receive event from C2. So now we have two pairs of the communication. The first pair is this C1 here, received from C2 here, can be paired with the EBT1, since the EBT1 is communicating through C2. So this is the first pair, the EBT1 with this receive event. The second pair is the EBT2 with this receive event. And the question here is, which send should the receive to be paired with? And we want to consider the priority. However, there are different options. Should we have the event inherited priority from creation? If that's so, this EBT2 was created under the context of high priority thread. Right? And so the EBT2 should be inherited that high priority. As a result, this is a high priority, this is a high priority event. However, this EBT2 gets synchronized before EBT1. As a result, we should be pairing with the low part, this EBT2 with this receive event. And another option is, should the event priority inherit from the synchronization? If we look at EBT1, the thread that synchronizes on this EBT1 is a high priority thread. As a result, we should consider, if we consider the inherited priority from the synchronization, the EBT1 should be high priority, and the EBT2, the thread synchronized on EBT2 is a low priority thread, so it's a low priority synchronization. And as a result, we should be uh, pairing with the high priority event. So we should be pairing with the EVT1 here. Now we have different options. So these are the options that and questions we need to tackle when we consider the priority in the message passing. And things get more complicated when we consider a selective communication. A selective communication is a primitive that message passing model can provide. A thread can synchronize on a set of potentially available events. And CML provide a primitive called choose. You can choose on a set of events from EVT1 to EVT2 up until EVTN. And CML will pick one of the event non-deterministically. And if none of the events are available, the thread that synchronizes on this set of events gets blocked. And that's how the selective communication goes. And let's see how the priority plays when we consider a selective communication. And we have another example. This example has three threads, have a high and medium and low priority thread. At the beginning, we have high priority thread sync on a send event and it send a value v1 to c1. Then high priority thread blocked, we switch to medium priority thread. The medium priority thread sync on another send event. It's sending a v2 to channel c2. And medium priority thread blocked. Now we move on to the low priority thread. Let's consider the low priority thread performs a choose. You try to choose between two receive events. So it can either pick receive event from C1 or it can pick receive event from C2. Both events are available because this receive event from C1 can be paired with this thread, high priority thread, and this receive event can be paired with this medium priority thread. So since both of them are available, we can pick either one of them. And when we considering the decision, we want to know following factors. First, we want to know the priority of the thread that performs the synchronization, and we also want to know the priority of the events that is synchronized on, and we also want to consider the priority of the choose pools, events in choose pools. And if we don't consider all of these events, which is CML currently doing, and it will try to pick either one of them non-deterministically. And if the CML pick the receive event from C2, then we are going to have we're going to unblock the medium priority thread. It's going to have the medium priority thread up and running. As a result, the high priority thread will never have a chance to pick again, and it's not going to making more progress after this communication. So this decision introduced a priority inversion, and we don't want that to happen. So this is something we also want to prevent. We want to consider when we introduce our priority schemes. So uh, our schemes want to integrate both free priority and event priority. This scheme to have rules about how the priority to be composed and to be compared. Our solution is a tiered priority scheme, and both events and threads as are prioritized entities. Thread priority uses to prioritize computation, and event priority uh, used to prioritize events in a selective communication. The, the goal of event priority is to give a final control over the priority between the threads of equal priority. And uh, the important part of this tier priority scheme is thread priority are given preference over event priority. So after we introduce this scheme, let's consider the example we have in our last slide. If we consider the three priority, the decision, if we made a decision by a three priority, then we know that the this pair this pair with the C1 is synchronized by a high priority thread, and the second pair synchronized the the thread synchronized on this send event is the medium priority thread. As a result, if we want to make the decision by the thread priority, we should pick the first pair. As a result, high priority thread get the chance to unblocked and will resume and up and running again. There's no priority inversion in this case. And next, let's consider to boost up a medium priority thread to the high priority thread. Uh, Now, since both threads have the same priority, we want to make the decision by event priority. We we have a primitive called send evtp, and this p will take a priority. The priority is integer. The larger the number is, the higher the priority are. And we can see this send event has a priority 10, and this has a 5. 10 is greater than 5, so we will be pairing the first pair. So we will be paired after we pick up the first pair. The high priority thread on the top gets unblocked, and it's up running again. So this is the example applying our tiered scheme, tiered priority scheme. And this tiered priority scheme gives us a power to express non-blocking synchronization, also known as polling. CML has no way to express polling. Consider the following code snippets. Here we have a polling function taking a channel, and it performs the choose between always event and receive event. Note that always event is to ensure the synchronization never blocked, and the choose in CML is non-deterministic. As a result, the CML may pick always event even if the receive event is available. And to perfectly behave as a polling function, we should pick the receive event whenever it is available. So in the CML, we can leverage event priority to achieve the behavior of polling by setting the priority of always event to the lowest possible. For example, to -1, and as a result, choose only pick always event when there's no other events available. And our system has a fully formalized semantics. In this semantics, we have an oracle. This oracle has a power to pick the correct pair in a communication. And we implement this semantics in PyCML. Then we perform some case studies. Let's see a case study in a termination in Swerve. Swerve is a web server. It's entirely written in CML, and the current issue in the Swerve is that it cannot guarantee the shutdown gracefully. And the reason is the Swerve has to pick between the shutdown event or accepting new connections. And so if the shutdown event gets issued, it, it might not be picked when there's available connections. As a result, shutdown gets delayed. We can add priority to shutdown events. The change is only 3 lines of code. After we adding the priority to shutdown event, we can see that as the number of clients goes up, the broken connection, which was introduced by the shutdown delays, stays consistent under prior CML, while in the original CML, we have more broken connections. Under the heavy load with 64 clients, we have 15 broken connections. And the next case study is a GUI shutdown protocol. We evaluate the response time of a shutdown protocol under the context of Xing. And Xing is a GUI toolkit in CML. We want to wait for all the widget to close up upon receiving a shutdown request. And since the choice has a non-deterministic selection, it will degenerate the response time because it will overlook a shutdown request. And the result is shown as a graph. These graphs on the top, we have a result from CML. On the bottom, we have the result from prior CML. We can see the response time is significantly faster in the prior CML. The maximum of the shutdown time has been reduced from 100 seconds to 40 seconds. And moreover, the variant of the shutdown time is far less than the CML. So these are only we conduct this experiment by only adding a priority to the shutdown event when we have achieved this benefit. Now, let's move on to a conclusion. Prior CML is an extension to the concurrent ML that introduced a priority to a synchronous message passing. Our next goal is to integrate prior CML on top of RT Milton. It's a compiler extension for real-time system from Milton. And so this is our today's talk. I'm happy to be here. Any questions?